Hello there, Physics 30. We are on the last lesson, last video of Physics 30. We're at the end. We're doing chapter 17 today in one day. And we're going to kind of see how things go. It's going to get weird. There's not a lot of information here that's going to make a ton of sense, but it gets into kind of more detailed ideas. So these first couple pages here are just telling you what you need to know from chapter or from the last unit. Pretty much all that you guys understand at this point. So chapter 17 is the fundamental forces here. All right, we have electromagnetic force. Its range is infinite. It's not really. It's very very large. It's kind of medium strength. Gravitational, the very very large, is the strongest over large distances. That's gravitational, the strongest over large distances. But then it's also the weakest at nuclear distances. So when we get into nucleons and electrons orbiting and all that stuff, gravity really is just not a factor down there, right? So basically, the very very large, you have gravity, and then kind of in between, you kind of have electromagnetic. And then the very, very small, you have the strong nuclear force, which keeps the nucleus together, and the weak nuclear force, which kind of keeps electrons, neutrinos, and all this kind of stuff, them, what they do. So there's kind of this concept between all those things. So those are the four fundamental forces of nature. All other forces are a result of either chemistry or this. All right. So particle physics is when we look at the actual particles themselves, and we try and break them down and see what things are made of and all this stuff. So the original particle physics was everything's made up of neutrons, protons, and electrons. But then what we started doing is we started basically taking high energy particles, okay, high energy particles, and accelerating them, and then smashing them together and seeing that they're converted. They're trying to basically kinetic energy is converted into mass, and then they create new particles some of the time. They smash, they destroy, they change nuclear bonds. It's kind of a lot. And so, what they basically, with the biggest one of these is called the Large Hadron Collider. It's in Switzerland. What it does is it gets basically can accelerate protons up to 7 tera electron volts, which means that then they smash two protons together, which means they have energies up to 14 tera electron volts can be examined, right? So they use large magnetic fields. It actually crosses two countries. It crosses from Switzerland into France and back into Switzerland. Okay, it's 100 meters below ground and it has a 27 kilometer circumference, right? It contains 4 detectors to analyze the products of the console. So it's 27 kilometers around, right? So you can do some quick math and figure out its diameter if you wanted to. But the idea is that you can't just go for a jog around it. It's 100 meters below ground, right? Straight down 100 meters. So that's kind of the idea. It was a huge, huge scientific thing. And what this has done is it's basically made all other particle accelerators just seem tiny because they're getting fractions of this much energy. Okay. All right, this video, watch it. It's super interesting. It tells you how the Large Hadron Collider works, how they accelerate things, how fast they get going, and then how when they get close to the speed of light, things get heavier instead of faster, and it's awesome. There's a couple other particle accelerators. There was a Tevatron. It was closed in September 30, 2011 because of budget cuts. This was the one named to the States. Okay, it was pretty good. It wasn't quite the same as LHC. And yeah. So then there's also a couple in Canada. There's one in Vancouver called the Triumph. There's also one in Saskatoon since these slides have been made. That's been built and it's pretty good too. It actually accelerates them in little rings. And then they accelerate separate in little rings and then brings them all into one kind of thing. It's kind of cool. So you get different angles and stuff like that. So anyways, what you're doing is you're accelerating invisible things you can't see, like protons, and you're smashing them together. Well, when you smash a proton with another proton, it's like you can just see what happens, right? So you have to create these detectors, and these detectors are cloud chambers. All right, these cloud chambers are essentially they have water vapor or something in it, and they also have a magnetic field on it. So when a charged particle moves through the air, it's going to ionize some of the molecules in its path, which is going to create vapor. So essentially what it is you get a particle, and some kind of particle is going to go through this. As it goes through, it's going to create little clouds. It's going to create little clouds as it goes through, ionized little particles, okay? And then what you do is you put a magnetic field across it so then you can tell if it's going to curve this way, then it was, was charged a certain way. If it was going to curve this way, then it was charged a certain way. And you can see that things that are neutral will go straight, things that are charged one way will go one way, and things charged opposite will go the other way. And it's just based on the left-hand, right-hand rule kind of idea, right? And what this allows us to do is it allows us to analyze, if something curves really, really tiny, right, then it's got a lower mass. If it's something curves larger, it's got a larger mass. Or if it curves really tiny, it's got a high charge. And so we can kind of tell by the curvature the charge to mass ratio, right? And certain things have a particular charge to mass ratio. So this is the idea. And so if the world was only made up of three things, it was made up of protons, neutrons, and electrons, you would see only three different things. You'd see straight, right? You'd see things go straight, basically, right? You'd see only straight for the neutrons. You'd see the protons do something like this, and you'd see electrons do something like this. And you'd only see little circles all the same size, right? So when they started doing this in like the early 70s with smaller particle accelerators, maybe even the early 60s, and so they basically said was that there is a concept of, well, we're getting all these different tracks. And since we're getting all these different tracks, we're getting all different kinds of particles and subparticles. Holy man, it's going to be crazy. And so they started discovering these things, right? They started discovering these things and showing them. So that's how cloud chambers work. Now, there's also gas chambers or bubble chambers. They appear the same way, except the opposite. It's already a tank of water, right? They're in a tank of water or something. It's highly pressurized to a certain thing. Not water, usually hydrogen, helium, all that kind of stuff. And when you send a particle through it, it's actually going to create bubbles instead of clouds. It'll create bubbles in the liquid. And you can, of course, see where those are. And so you see the bubbles form on the particle's pathway. Okay, same kind of concept. So what we can do is we can always see basically by looking at, we know the magnetic field, right? We know the magnetic field. We're going to erase that so you guys can actually see it. We know the magnetic field, we know the radius, we also know the velocity because we're the ones accelerating to a certain velocity, right? So we can know all those things, and it gives the charge to mass ratio. So particles with smaller charge to mass ratio will move at a higher radius of curvature, right? So a heavier particle, like a proton, will move like this. So a smaller, lighter particle, like an electron, will move like this, right? And so there's kind of protons and electrons, right? So we kind of have to analyze that. Oh, I hit the wrong button. There we go. Right, so we can look at this tracks like this. So what we have is to analyze this path right here, okay? And it's asking for which one's an electron, positron, and a proton. So an electron should have a small circle, right? It should have a small circle. Okay, so that's A or B, the electron. A positron is C. A positron is the opposite of electron, so it'll curve the opposite way because it's opposite charge, but should have the same size circle. And a proton will still curve, but it's so much heavier that's going to curve much less. It's going to get much bigger circle, right? Okay, so those are kind of an electron, positron, proton. Okay, where a neutral particle decayed. So what we're having is there's nothing here, and then all of a sudden right here, a positron and electron to appear. And since a positron and electron appear, what that means is that something that was neutral decayed into those two things, right? Same idea here, we had a new positron in here. So there's no path, and all of a sudden it's split into B/C because we're in a bubble chamber and non-charged particles leave no trail, right? Okay. So we get to quantum theory and discovery of the new particles. So we're talking really small. So Dirac combined Einstein's relativity theory with Schrodinger's wave equation and predicts the existence of antimatter. Okay, antimatter, opposite of matter. When antimatter and matter come together, they smash, and it's really bad. Okay, and so Anderson photographed the particle track of a positron in a cloud chamber to prove that antimatter existed. When the particles and their antiparticles collide, they annihilate each other and create two high-energy photons in opposite directions. And so basically we have electron positron annihilation happens in stars, and the energy of each of these particles can be calculated using E equals mc squared with the mass of an electron. So you kind of get this idea where we have these energies and these photons coming together. So we have antimatter and matter hitting each other and causing pretty serious explosions and photons coming out of it. All right. Okay, so it was a bubble chamber that allowed physicists to determine that antimatter does exist. Antimatter again has an opposite charge, but it contains the same mass as regular matter. And when they collide, they annihilate, even leaving only 2 photons. So there are actually 2 photons created from this collision, and they must travel in opposite directions. Otherwise, the law of conservation will be annihilated. So what is the minimum energy created when a proton collides head-on with an antiproton? So the minimum energy, right? So that would be, we're looking for energy. So that's E equals mc squared, right? And since we have a proton and an antiproton, we're going to have m is 2 times the mass of a proton, right? Mass of a proton being 1.67 times 10 to the negative 27, right? Okay, so E equals 3.34 to 7 times c squared, so times that by 3 to the 8 squared, and we're going to get the energy is 3.006 times 10 to the negative 10 joules, right? Which again doesn't seem like a lot, but it is when you're considering you're just having a one single proton and one single antiproton creating this. So, okay. So this is used in PET scans. Okay. I'm sure you guys have heard of CAT scans. PET scans are a very similar idea. We put tracers into the body that are radioactive, and then they emit positrons in the body, and the positron then goes parannihilation electron. That produces gamma rays, and then the photons are detected by a detector. So you basically put in something that's going to create positrons, going to find some electrons, destroy them, and then you have a detector that's going to detect them, and then you can actually see the makeup of whatever's going on. So computers then analyze all this kind of stuff, and they create an image and kind of the idea. So you kind of get the idea of where this leads into biology and all this sort of stuff. So anything to do with like scans or anything like that is based off of physics and all this kind of stuff. Okay. So looking at the standard model, you guys are supposed to understand the standard model as best you can. But the standard model basically has 3 ideas. They have quarks, leptons, and bosons. All right, so the first idea is that quarks are what make up protons and neutrons. All right, and they create hadrons. Hadrons are a classification of their own, but quarks that make up normal matter must be first generation quarks. There's no antiquarks generation since they all kind of destroy each other. So quarks are smaller inside of a proton, okay, and a neutron. All right, there's nothing inside an electron. Electrons still considered fundamental. All right, and you'll see kind of some information about quarks right here: up quark, down quark, anti-up, and anti-down. So the first generation quarks are these 4, and the only 2 you can use to create regular matter is the up quark and the down quark. No anti-quarks. All right, so Rutherford kind of started this idea, but then it was finished by Richard Taylor and others in the 1970s at Stanford. Okay, they ended up winning the Nobel Prize, and he actually was originally from SNAT, Dr. Taylor. And so they said is, okay, well, basically if I look at a proton, right, a proton is a particle, right, it has a positive charge, and it's actually it's up, and a down quark all kind of meshed together, and they are all linked in a certain way. So that's what it is. And the reason I know it's an up, and a down is because an up has a charge of 2/3, an up has a charge of 2/3, and a down has a charge of negative 1/3. So proton is 3 quarks, 2 ups and a down. That gives me a total of positive 1. A neutron is an up and 2 downs, right? An up and 2 downs, which is positive 2/3, and then minus 1/3, which equals 0. And so quarks have fractional charges. Okay, quarks do not exist on their own. They combine to create hadrons. All right, you can also have antiprotons. So an antiproton has all the antiquarks that a regular proton does. And so it's an anti-up, an anti-up, and an anti-down, which gives me a negative 1. Okay, there is things that are like a down, down, down. Okay, and that's its own special particle. And you have all these different combinations. And so instead of really giving them all specific names that you need to memorize, they kind of just put them all into one single category called hadrons. All right. So first generation quarks make up normal matter. So this is our generation. So if you kind of follow this chart, so first generation quarks up and down, they make up normal matter. But then there's also more quarks. There's the second generation, which is the charm and the strange quark, and the third generation, which are the top and the bottom quark. And so now that instead of just having the combinations of ups and downs, you also have the combinations of up, charm, top, down, strange, bottom. You can actually combine all of them to create different particles. Now, a majority of them only last for milliseconds or less, and because they're not first generations, right? So anything to do with the charm, strange, top or bottom doesn't really exist very often. Okay, but you notice that the mass changes, right? The top, look at the mass compared to a up quark, right? Okay, so an up quark is 4 big electron volts, and a top quark is 174,000, right? So that's kind of the idea, is that quarks make up hadrons, and they're kind of the idea that most matter is protons and neutrons, which is ups and downs only, right? Anything beyond that is going to just destroy itself or destroy something else because of its large mass. So they can be 2 quarks, but generally they're going to stick with 3. But there is this idea of a 5 quark combination called a pentaquark, which they've kind of, there's mathematically, it's called a theta plus, okay? It's been hypothesized to exist, right? And so it's 2 ups, 2 downs, and 1 anti-strange quark. The reason it's considered possibly existing has to do with the fact that it is mathematically a part of the system that we've discovered. Like, it's just the kind of the same idea with the chemistry and how we could predict where elements should be. Well, the same idea with the pentaquark is that it should exist, we just haven't found it yet. And so 2 ups, 2 downs, and anti-strange. The charge is 2/3 plus 2/3 minus 1/3 minus 1/3 plus 1/3 is this positive 1, hence the name the theta plus quark, or the theta plus hadron, depending on how you're going to call it. So, all right. So then there is this idea. So Standard Model contains quantum mechanical model and explains all known particles into categories. And so in like the 70s and 80s, when they're smashing all these protons together, or neutrons and protons, it doesn't really matter what you were smashing together, they kind of discovered basically a new particle every day. It seemed like they discovered tons of new particles, and then when they first went to Large Hadron Collider, they've discovered a whole bunch more particles, and they just realized that all of these particles were just different combinations of these, right? And so they just said, okay, we're going to call all those things that are combinations of quarks, we're going to call them all hadrons. Okay, so the hadrons are made up of quarks. All right, that's protons and neutrons and all their friends. All right. Then there's leptons. Leptons are some particles that kind of are special. All right, these are electrons, positrons. Okay, neutrino and antineutrino. Leptons don't really they don't break down. So if you take electrons, you smash them together, they don't do anything generally. Now, if you do with enough energy, things get weird again. And then there's bosons. Now, bosons are considered exchange particles, and they're what cause forces. So the idea is that bosons are the things that cause forces. So, for example, for the electromagnetic force, the boson is the photon. The photon is what causes the electromagnetic force. It moves it, it does it. Right? For the weak nuclear force, it's called W plus minus. All right? And the strong nuclear force is the gluon, right? So that's why, two protons, the reason that they're attracted to each other is because they're trying to share a little gluon. And so by sharing it, they pull each other together, right? That's the idea. Now, gluons do not exist outside of the force, and the force doesn't exist without gluons. And so, all right. And so then, of course, they predicted that since there is the photon, which we see lots of, and we can measure the W plus minus, and we can also have seen gluons, we predicted that there should be something called a graviton. Okay, they call it graviton, and the idea is that that's what causes gravity. It goes between particles of mass, so it actually creates mass in general. All right, and so the graviton doesn't create mass, it interacts with mass. Graviton interacts with mass. Then they kind of went to, okay, well, what creates mass? Why does mass come as mass instead of energy? And so then they predicted the Higgs boson, right? Again, they mathematically predicted the Higgs boson. I believe they have good evidence for it now. All right. And they say it's basically the Higgs boson is what is actually creating mass, like why things have mass. All right. And without the Higgs boson, the whole system falls apart. So now it's kind of been discovered. All right. Yeah. And so it's kind of the God particle, right? They've been looking for years, and they finally have found it. And it's kind of this idea. It really gives you it makes the whole system work, right? It's the same as how if you're trying to get the whole body to work and the whole system, and then you take out and then you just say no oxygen. Well, then the human biology doesn't work without oxygen, right? Because oxygen is so present in everything, or carbon, right? Same concept with this particle matter of a particle model of matter is without the Higgs boson, it doesn't work. You need the Higgs boson, and so they have essentially found it. All right, so that's the end of Physics 30, you guys. This is a lot of information. I don't expect you guys to understand every ounce of it, but it's something to be interested in, have a good idea to go with, and it just, if having a fundamental knowledge of particles and how they work can always lead to more understanding of higher level math or higher level physics or even higher level chemistry and biology, depending on what you're looking at. So I hope you guys enjoyed this so far, and this is the last Physics 30 video. Have a good one.